as mentioned, we're going to look at a chi-square. Now this is actually two different things. You can also write it as the Greek variable chi, which looks a lot like an x, and then the square for chi-square. And so what we want to do is kind of examine how we're going to look at that count data. And we'll start with the chi-square test of independence. Okay, so we'll look at that one first. And again, you know, what we want to do is just look at a simple case. And so suppose, you know, I have variable 1 and I have some levels A, B, and then I have variable 2 here, and we'll say these levels are C and D. You know, suppose there's 10 there, 20 there. We'll put maybe 40 here and 20 there. So what do we get? Is that 90 overall? So we'll make that a 20. So here we had 40 here, 60 there, 60 there, 40 there, to make a total of 100. And the way we look at this is we notice that, yeah, this is definitely not on the surface independent, in that if I look here at this row, it looks like A and B are split equally, 50-50 or literally 20-20. But if I look at this bottom row, it seems to matter what row I'm in because A is twice as big as B. So on the surface, they look dependent. It does matter what row I'm in. Or the same thing, I could say it matters what column I'm in, because if I'm in column A, then D is twice as big as C, but if I'm in column B, then D is the same size as C. And so, you know, it definitely on the surface looks like they're independent. The way we're going to check that is we're going to come up with, for these totals on the ends, the 40, the 60, 60 and 40 here, we're going to come up with the perfect independent situation. So I write 40, 60, 60, 40 that we had there already, and that was a total of 100. And what we're going to do is fill these in with the correct number that should go in here. And so what I need to have is of this 60, I need 40%. So you see this row has 40%, this row has 60%. So I need this these two blocks to make that work that way for this same 60. So 40% of 60, that would be 40%, right? Now, how did I get 40%? Well, it's 40 out of 100 and 60 out of 100, so 60%. So you see what I'm doing is I'm figuring out the percent by taking this number divided by the total. And so it's easy to see here that that's 40%. And then I want 40% of 60. So how do you do that? Well, you see 40% of 60 is just my 0.4 times 60. But if you look at all the numbers involved, really what we did was we took this 60, we're multiplying by 40 and dividing by 100. Okay, so you look at the 40 over the 100, that's 40% times my 60. And then 60% of 60, okay, I'm taking the 60, I'm taking this other 60 and dividing by 100, and that's 60% of 60. And the same thing works here. So you see what you do is you just look for this box right here, you look at what row it's in, what column it's in, take those two numbers, multiply them together, so 40 times 40, divide by the total. And so we'll have here 40 times 60, divide by the total. And what that becomes then is my perfect independent situation would have, I'd have 24, whoops, I still don't know why that does that, 36, and then 16, and 60% of 40 is the 24 again. And notice these add up to 40, 60, 60, 40, and 100. So this is my A and B and my C and D for my expected. So we have here our actual data, and here is what we would expect or expected if they were independent. So we start with our actual data, but we look out here at the margins, at these totals on the ends, and from those we build something that's perfectly independent. And so you see 16 is 40% of 40, 24 is 40% of 60, and 36 and 60 work that same way for 60%. 36 and 24, sorry, work that same way for 60%. So that's our expected. And then what the chi-square does is it looks at the difference of those two. Now in Module 2, we looked at this normal distribution idea, and we want to, we looked at approximating things with a normal distribution. Well, we do the same thing again here, is we approximate with a normal distribution. And so in this case, that the way we approximate these is we get what we call a chi-square variable from squaring a 0, 1 normal, a standard normal variable. And so it's the idea of our data, so 20, that number there, minus our expected number, or a hypothesized number, 24. That's very similar to what we did. Remember, we had our in Module 2, we had our x bar minus mu for a normal distribution approximation on something like this. And so there's our x bar minus mu, and so we have our 20 minus 24, and yeah, I still don't know why that scrolls. I haven't figured out what I touch or anything, so I don't know. And then we divide that by our standard error. Now in this case, we aren't going to go into it, but actually the standard error here, a good expectation for the standard error is actually that number 24 in this case, well, except the square root of that. So we would have the square root, but we're going to square everything. So here we square that and we divide by 24. And so we really are taking, again, the difference in the means, our data mean and our hypothesized mean mu. So the 24 is really a hypothesized mean. So we're really taking the difference in those, divided by the standard error, but squaring everything. So my chi-square number is that, and then plus, do the same thing with the 16. 16 minus, 20. It's getting kind of ugly, but 20 minus 16 squared over 16 plus 36. Oh, I keep looking at the wrong one. Sorry. 40 minus 36 squared over 36. I'll get it right this time. 20 minus 24 squared over 24. So there's our chi-squared number, and it's that simple. So the math here is really pretty easy. We need to, we take our data, we have to add these up to get our totals. Then we have to take those edges and multiply in order to get our expected values. So we have to do some addition, we have to do some multiplication over here, then down here as just the result of my multiplication. Then we have to do a little subtraction and more division in the squaring, which is multiplication. And so we get that chi-squared number. And then once we have that chi-squared number, well, we look up, and here we just have to look it up. We look up that probability that our chi-squared number, so our chi-square is greater than or equal to, I'm going to call this, I guess, chi-square hat, just so it's, chi-square hat. We have to look up that probability, and if, what we want to know is, well, is that bigger than 0.05 or less than 0.05? And so it's that same question we started asking is, it's all about 0.05. We need to know what does that equal, and then we check against 0.05. Okay, so we're going to do that every single time we do one of these. We're going to check it against 0.05, except for one particular situation in, I think it's chapter or module 4. And so we check it, and, so we'll have to look one of these up, and that's what we do. We build a template that will look these up, and we get our answer for that. But that's all there is to it. Now, I haven't mentioned degrees of freedom. Degrees of freedom. Okay, so we have to worry about that. And the degrees of freedom is just the number of rows minus 1 times the number of columns minus 1. And that gives us our degrees of freedom, and we need to look at that when we look up our number. So that's in your textbook, and so that's an introduction to what we have to do for this chi-square test of independence. It doesn't matter how many rows or columns we have, we just fill everything in the same way, evaluate this chi-square number the same way, and then the only difference in looking it up is our degrees of freedom. So that's what we have for chi-square test of independence.